Alright, this is card 102, and we're going to start talking about similar figures, more specifically similar triangles. So, let's start with the main sentence about similarity, or a description. Two objects that have the same shape but do not necessarily have the same size. Did I spell that right? Yeah, have the are called similar. And the symbol for similar is just the top of a congruent symbol, right? That curly thing. So they have to have the same shape, but they don't have to have the same size. They could, but they don't have to. All right? Let's see what else. All right, so polygons, that's any shape, like a triangle or a square or a rectangle, right? Any shape are similar if they're corresponding angles are congruent and the ratio of their corresponding sides are in proportion. Okay? Let's see now. Alright, I think now we can just turn this over and draw a picture of an example of two figures that are similar. Okay? So what I'm going to do is, I gotta get my protractor. Alright, and my ruler. So I'm going to draw two similar triangles. Alright? I'm going to draw that length about 1.5, and then I'm going to come up a certain amount, like 1 inch that way, and then this dimension will be about 1 3/8. Alright, so that's my first triangle, and the next one I'm going to draw is going to be similar but bigger. Okay? So, we have these two triangles, and if they're similar, let me just see something. Why doesn't it say anything about the angles? Okay, so it said that corresponding angles were congruent. So let's call this triangle A, B, C, and let's call this D, E, and F. Now if these two triangles are similar, the angles that are corresponding are congruent. So angle A would be congruent to angle D, that's the corresponding angle. Angle B would be congruent to angle E, and angle C would be congruent to angle F. That's one of the properties of similar figures. Corresponding angles are congruent. Now we know they're different sizes, okay? But the other fact is that their sides, their corresponding sides, are in proportion. All right, so let me explain what that means. If we have a 10 here, and a 6 here, and a 7 here, and let's say this side right here was a 20. Well, to get from 10 to 20, we multiplied by 2. So that means these other sides, you have to do the same thing to get what they are. So 6 you would multiply by 2 to get 12. 7 you would multiply 2 to get 14. So the sides are in proportion. Okay? Now, let's write down a couple of facts about this. We know that really we should fix something here because I made this bottom piece the longest, so we should really make this look a little bit more proper. So sorry about that, but we're going to need to do a little erasing. Let's see. I just want to fix, we did it right, I just want to fix the sides because I want to make the longest side the biggest number. So let's make this one 10, this one 7, and this one 6. So then let's say this bottom here is 20. So 10 is to 20, as 6 is to 12, and as 7 is to 14. That means the sides are in proportion. Okay, they're in the same ratio. So the first thing we can say is that the angles are all congruent. So angle A is congruent to angle D. Angle B is congruent to angle E. And angle C is congruent to angle F. Now, all the sides are also in proportion. So, alright, so the way that we write this is we could say that the ratios are equal, which means that we would put the side lengths over each other. Alright, so when we're saying that the corresponding sides are in proportion, it means that if we take the sides that are corresponding and make them into fractions, those fractions will all be equal. That's what it means that the proportions are, that they're in proportion. So for instance, AB is 6. If we put that on the top and we put its corresponding side from the other triangle on the bottom, which is DE, so it would be 6 over 12. That would be equal to BC over EF, right? Because those are two corresponding sides. So 6 over 12 equals 7 over 4. I mean 7 over 14. So it equals BC over EF. They're both equal to a half, right? And also it's equal to this side of the small triangle over this side of the big triangle, 10 over 20, which is also a half. So you can see that all the corresponding sides are in proportion. They're all, they're all the same ratio or the same fraction, right? This side was AC and this one is DF. So if we put in numbers for this, 6 over 12 equals 7 over 14 equals 10 over 20, which they all equal the ratio or the proportion 1/2. Okay? And that's true of all similar figures. Let's put one more thing on the front here. Let's put the ratio of the corresponding sides is called the scale factor. Okay, so that fraction that they're all equal to, that 1/2, is the scale, it's called the scale factor. Okay, let me just see if there's anything else that's really, really important. So let's just write over here that, well, triangle ABC is similar to triangle DEF. Okay? And that's plenty of info for that card. All right, that's a good start for similar triangles. Now, in the next card, we're going to start, I believe we're going to start talking about how to prove triangles are similar. Just like there were methods for proving triangles congruent, well, there are methods for proving triangles similar. Let's see. First, let's write down some additional facts about similar figures. So let's see, how do I want to put this? If two polygons are similar, and then let's put a colon there. Okay, and let's now list some additional properties. So if two polygons are similar, then their corresponding let's see, sides altitudes, medians, diagonals, comma, angle bisectors, and perimeters are all in the same ratio, are all in the same ratio, or in other words, proportion. So not only are the corresponding sides in proportion, but corresponding altitudes, medians, diagonals, angle bisectors, and perimeters are all in that same proportion. Okay? Additionally, number 2, the ratio or proportion of their areas is equal to the square of the ratio of their corresponding sides. All right, so Okay. I'll give you an example of that on the other side. Okay. And then finally, number 3, the ratio of their volumes sorry, let's keep it in the same deal here. The ratio or proportion of their volumes is equal to the cube of the ratio of their corresponding sides. So let's do a couple of examples on the back. All right, so let's do an example of the first one. All right, so if we had something like, if the sides of two similar triangles are in the ratio 4:9. What is the ratio of their perimeters? All right. And the answer would be 4:9. Okay? Because the perimeter is in the same ratio as the sides. Let's just quickly split this thing up into 3 sections. So if I got 4 in an inch, I'm like 1 1/3. So figure I'm like here, and 1 1/3. That's close enough. Just going to divide this thing into about 3s. Okay. And I'll put one example in each one. So now this will be an example of the second one. Let's see. We talked about areas in the second one. So if the sides of two similar triangles are in the ratio of 3:5, right? And we can write that as a fraction, 3/5, right? It doesn't matter. That means 3/5. It's a ratio. It's like a proportion. Find the ratio of their areas. And so the answer to this one would be, it's the square, right? We square these numbers, so 9 to 25. Okay, so the area isn't in the same ratio, it's in the square of the ratio. And then for volume, it's in the cube of the ratio. And that should be easy to remember because area is always squared anyway and volume is always cubed, so you can always remember it like that. So if the sides of two similar triangles are in the ratio of 2 to 3, find the ratio of their volumes. And so my answer is going to be, I got to cube both of these numbers. So 2 cubed is 8. I don't want to write a colon there because I don't want you to confuse it with the colon in the ratio. So it's 8, and then 3 cubed is 27. So it would be in the ratio of 8 to 27. Alright? So that's good enough for the next card on similar figures. Now, what I want to talk about is proving triangles similar. Now this is where we're going to talk about the methods of proving triangles similar. Okay? Just like there's methods for proving triangles congruent, we have methods for proving them similar. Oh, by the way, that was card 103. So now we're on card 104. Okay. There are 3 methods for proving triangles similar. I'm just going to pull out the congruent, where we talked about the congruent card, so I can see the format I used. So I'd like to use the same format. Okay. Card 51 is where we talked about congruent triangles. So, the first method is called AA, right? Which you should know by now stands for angle, angle. Okay? And let me see for a second here. Okay. Now the second one is SSS for similarity, because remember there's an SSS for congruency, so we have to differentiate between the two. This one is for similarity, but it's still side, side, side. Alright, and then the third one is SAS for similarity, which is also, there's one of those for congruent, so we have to again say for similarity. So if we can prove 2 triangles, if we can do SSS or SAS on two different triangles, then not only do we know they're congruent, but we also know that they're similar. And this one obviously is side, angle, side. Alright, so those are the 3 methods that we're going to discuss on the next few cards. So that's good enough for this card. That's like the introduction to it. Now let's start with, let's do a card for each method. Let's see. Alright. If 2 angles of one triangle, this is for the first one, AA. If 2 angles of a triangle are congruent, to if two angles of one triangle are congruent to two angles of another triangle, to two angles of another triangle, comma, then the triangles are similar. All right, and let's draw a picture of this on the back. So, let's draw two similar triangles. I'm going to use the centimeter side this time. I'll go like 5-ish, and then I'll go up, let's say about 3 at an angle about like that. And then this one ends up being about 4.5, it looks like. Okay, now I'll make this next one about half as big. So this triangle, I went 5 on the bottom, so now I'll just go 2.5. And then I went up 3, so I'll go up about 1.5. And then I'll just connect the last two sides. Alright, so I got two similar triangles here. So let's call this first one A, B, C. And the second one will be D, E, F. Alright, so for example, if I can prove that A is congruent to D and B is congruent to E, if I do that, then I know that the two triangles are similar. So let's write a statement here. If angle A is congruent to angle D and angle B is congruent to angle E, then triangle ABC is similar to triangle DEF. Alright? That's what we got for that one. Alright, let's go to the next card. So that's AA. Oh, that was card 105. Now we're on 106. Okay, let me see something here. Oh, so here's how SSS for similarity is different, because we're not proving the sides are congruent. When we're talking about similarity, we're showing that the sides are in proportion. Okay? So if the three sets of corresponding sides so all three of two triangles are in proportion, comma, then the triangles are similar. Okay, so let's see a picture of this. Again, if we draw two similar triangles, this time I'll make this bottom 6 and this bottom 3. Then I'll make this 3 and this 1.5. And then I'll just connect these sides. So they're close enough to similar. Just as long as they look the same, we'll say that they're close enough. Okay? So let's say I got A, B, C, and D, E, F, right? So if AB over DE is equal to BC over EF is equal to AC over DF, then triangle ABC is similar to triangle DEF. Okay? So that's that one. Do I want to put this one? Yeah. On the front here, put let's see, how do I want to put it? Let's put it right here. SSS for similarity. And on the front of this 105, let's put AA. Okay? And then our last method, which has to do with proportions. Anytime you see an S in similar figure methods, it's for the sides are in proportion, not congruent. Okay? So this is card 107. And it says, if an angle of one triangle or an angle of a triangle is congruent to the corresponding angle of another triangle and the lengths of the sides including these angles are in proportion, comma, then the triangles are similar. Okay, and this is SAS for similarity. And when we're talking about similarity, the S's mean that the sides are in proportion. Now you see how this says the sides including these angles? That means the angle has to be in between the two sides that you're talking about. Alright, just like for proving triangles congruent. So let's see an example of this or a picture to go along with this. I'm just going to draw the same picture I usually do. I'll do 0 to 6 again, 9 to 12. Then I'll do 3 and 1.5. And then I'll just connect these sides because it doesn't really matter what they are. So I already drew the other two sides. Now, ABC, D, E, whoop, F. Now I have to make sure I didn't do that on any of the other ones. No. Okay. So let's say A is congruent to D. So if angle A is congruent to angle D, and it's the sides that are that include the angle. So these two sides have to be in proportion. These two sides have to be in proportion to these two sides. You see, they're the sides that include the angle. So, and AB over DE equals AC over DF, then triangle ABC is similar to triangle DEF. Okay? So that's that for similarity. Let me just see if there's anything else I want to add. Let's see. I don't think I want to add anything else to this. Okay, that's good enough for that. Let's see. No, I don't need this. This is just examples. Okay, we're going to move on to the next topic, which is mean proportional in a right triangle. So this would be card 108. Okay, actually there is one more theorem that kind of has to do with similar figures. And this theorem says if a line is parallel to one side of a triangle, and intersects the other two sides of the triangle, then the line divides these two sides proportionally. Alright, and here's what we mean by this. Okay. So we have this triangle. Alright. Okay, so we have a triangle. Let's call it ABC. And then what we do is we have a parallel line, we have a line that's parallel to one side of the triangle and it intersects the other two sides. So for example, it could be parallel to this bottom line, right? Like this. And it intersects the other two sides. See how it intersects these two sides and it's parallel to this side. So that's what that first part said. Let's say it intersects here at D and here at E. And it's parallel, so we know that this segment is parallel to this segment. And it doesn't have to be in the middle of these lines, okay? That's the mid segment, but this doesn't have to be in the middle. What it says is that if okay, so if segment DE is parallel to segment AC, then we can say that these pieces are in proportion. So then BD over DA is equal to BE over EC. And that can help us solve all types of problems, which you'll see plenty of in the weeks to come. Okay? But you must understand that theorem. So let's put that one aside. And now we can talk about what's called mean proportionality and the mean proportionality theorems. So this would be 109. Okay, let's see. What's the first thing I want to say about mean proportionality? Let's see. Okay. All right. So I'm going to go right into the theorems on mean proportionality rather than giving you this definition of mean proportionality, because the theorems are what's most important. So the altitude to the hypotenuse of a right triangle forms two triangles that are similar to each other and to the original triangle. All right. So let's show you what a picture of this looks like. All right, if we have a triangle, okay, and let's say that this is a right triangle. Okay, and it's triangle A, C, B, or ABC. Now, and let's say you have this altitude or height drawn into the right triangle. Okay, so what that means is that this is also a right triangle, and so is this one, right? So the altitude up to the hypotenuse of a right triangle forms two triangles that are similar to each other and to the original triangle. So you see these three triangles? You have this little one here, this medium-sized one here, and then you have the big one. They're all similar to each other, okay? So in other words, let's call this intersection right here D. So triangle ACB is similar to triangle ADC, which is similar to triangle CDB. Okay? That's what it says. That's the first theorem involving mean proportion. Let's do the next one. This will be card 110. Let me get a sharper pencil. I'm going to sharpen this thing. Alright. Now, the altitude to the hypotenuse of a right triangle is the mean proportional between the segments into which it divides the hypotenuse. Okay, so what we get is called the altitude rule. And that means that, well, the verbal definition would be part of the hypotenuse divided by the altitude equals the altitude over other part of hypotenuse. Okay? And I'll show you what a picture of that looks like. Let's say we have a triangle. And actually it's supposed to be a right triangle, so I need to fix this thing a little bit. Okay, so this is a right triangle, and it's triangle ACB or ABC again, and we have this altitude, right, which forms two more right triangles that are all similar to each other. Well, the altitude rule says that, let's say this is D, one part of the hypotenuse of the big triangle, so let's say AD, over the altitude CD equals the altitude, this one CD, over the other part of the hypotenuse DB. So one part of the hypotenuse over the altitude equals the altitude over the other part of the hypotenuse. That's what the rule says. And that's only for this right triangle thing, when you have a right triangle and an altitude drawn down from the right angle. Okay? So you may have problems involving that theorem. Now let's look at 111. So this is card 111. And this is our final mean proportional theorem. Each leg of a right triangle is the mean proportional between the hypotenuse and the projection of the leg. On the hypotenuse. And this is called the leg rule. And the way that we can describe this rule in words is hypotenuse over leg equals leg over projection. And we'll see what that means on the other side. Okay? So let's draw a picture of our triangle here. So I'm trying to draw another right triangle. All right. So let's say this is triangle, again, ACB or ABC, depending on which way you read. And let's draw that altitude. So as you can see, mean proportional problems always deal with this same type of a picture where you have this right triangle with an altitude drawn down, forming two more similar right triangles, okay? They'll always deal with this type of a picture. So, how do I want to say this? Is there a nicer way to say this? Give me 1 second. Not really any nice way to put this. So we can have two formulas that will form. So we can take the hypotenuse, right, which goes first, and we have to divide that by the leg, okay? So remember, this is the hypotenuse and then there's two legs. So let's choose this first leg, AC. So there's going to be two formulas that you can set up here. And that's going to be equal to the leg that we chose, AC, over the projection of that leg. Now, if you project AC onto the hypotenuse, all you're going to project is this distance here. So the projection of this leg right here, if you can see that its distance in the x direction is just from here to here. So that's like its projection on the hypotenuse. Okay? So, oh, there's a D here, obviously. So then it's AD. Or we could have the formula, again, we use the same hypotenuse, AB, the hypotenuse of the big right triangle, over, now instead of choosing AC, let's choose the other leg, okay? which is CB, and that's going to equal CB over, and if I project CB onto the hypotenuse, what I get is BD, or DB, doesn't matter. Alright, so when you project AC onto the hypotenuse, what you get is AD. And when you project CB onto the hypotenuse, what you get is DB. Okay? So those are the two formulas for mean proportionality. Now, I just want to check something because I might want to add something. Okay. We're going to do one more card, so we're just going to have to renumber a couple of these, which is not going to be a big deal. Alright. So, what we're going to do is, let me just make sure this is right. Okay. We're going to make 109, 110. We're going to make 110, 111. And we're going to make 111, 112. And we are going to put a card 109 in there. It's going to be a new card 109. And this is where I'm going to put the definition kind of mean proportional. Okay? So, let's see. This is the definition of mean proportional. So the mean proportional of two positive numbers and let's just call them A and B, is the positive number X such that A over X equals X over B. Okay? And when solving, we would get X equals the square root of A times B. Okay? Because you would cross multiply and you would get X squared equals AB, and then you would take the square root of both sides. So, what we have basically is the formula they use is they say the extreme over the mean equals the mean over the extreme. And let's put in a little thing down here. Notice that the X value appears twice. In the means positions. Alright, and let's see, that's really it. On the back, let's just do this so you can see. So if I have A over X equals X over B, that becomes x squared equals AB, right, if I cross multiply. And then I would take the square root of both sides, and then this would cancel with that. So then x would equal the square root of AB. So that's how we get that x equals AB thingy. Okay? So you could stick that in 109. Okay? Let's see. Now we're going to talk about the Pythagorean theorem, which I know you all know and love. Okay. Just give me 2 seconds. Okay. Now, we are on card 113. 113. We're getting there. We are getting there. It says, in a right triangle. That's very important because a lot of people forget the Pythagorean theorem is only for right triangles. So in a right triangle, the square of the length of the hypotenuse. Oh, wait. Yeah, we could put this. The square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. All right? So what we have is the Pythagorean theorem. And that's c squared equals a squared plus b squared. And let's put where c is the hypotenuse, a is a leg, and b is a leg. Okay? Now, there's another way to write this theorem which you have to know, and it says that if the square of the length of the longest side of it, okay, we could say if the square of the length of the longest side of a triangle is equal to the sum just to keep things the same, I'm gonna change the word equal to a symbol, is equal to the sum of the squares of the lengths the other two sides, comma, then the triangle is a right triangle. So it's kind of like the Pythagorean theorem in reverse. Whoop, not then triangle, then the triangle is a right triangle. So you can use this second theorem to prove that a triangle is a right triangle. If you can show that the longest leg squared is equal to the sum of the other two legs, if you can show that the longest side of a triangle squared is equal to the sum of the other two sides squared, then you just proved it's a right triangle. So that's why they throw that one in there at you, okay? Because it's very useful sometimes. Now, I just want to see if there's anything I want to put on the back, but not really. Let's see. Don't really care about that. Alright, I guess we could draw a quick picture on the back. Let's draw a right triangle. Just any right triangle will do. And I just want to identify some of the parts to make sure that you're aware of them. So you should know right angle by now, and the longest side, the side across from the right angle, is the hypotenuse, and the other two sides are considered the legs. So, and you should know that c squared equals a squared plus b squared, where c is the hypotenuse, a is a leg, and b is a leg. I think that pretty much covers it. Okay? So let's see what's next. Let me just mark that one off.